So we want to talk about the 3-4-5 triangle. This is something that when you go to a normal maths class, it's confused by a whole lot of theoretical maths. It's called the theorem of Pythagoras, and the theorem of Pythagoras says the square in a right-angled triangle, the square on the hypotenuse is exactly equal to the square on the other two sides. Now, most students in a school setting, when you say that to them, their eyes glaze over and they think, why in heaven's name do I need to know about that? The reality is, however, lots of people need to know about right-angled triangles every day of their life. So builders use the 3-4-5 right-angled triangle often every day of their lives. Farmers use it, people building fences use it, all sorts of tradespeople and DIY people use the simple right-angled triangle every day of their lives to make sure that something is either vertical or at right angles to something else. Let me show you how it works. So we have here in the middle a little right-angled triangle. Now the sides, I've drawn it on graph paper so you can see the sides. That's 4 along that way, 4 units. It's 3 units along that side, and it happens to be 5 down that side, as you can see, because I've meshed it up on the paper. Now, as is often the case in numeracy and mathematics, there is some complicated theories, but behind those theories is something which we can apply every single day. So this is a right-angled triangle. That side is 3 units long. Let's call them 3 centimetres. Now, the Pythagoras' theorem talks about 3 squared. Now, some people have difficulty with squaring. 3 squared is just 3 that way times 3 that way. So I've drawn it in real dimensions. 3 times 3 is 9, and you can actually count up those spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that gives a visual representation of what 3 squared looks like. 3 is 3 times 3, and there it is 9. On this side at the bottom of the triangle, that's 4 units or 4 centimetres, and 4 squared is represented by 4 times 4, which you can see is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's that square there is 9, that square there is 16. Now, on this dimension there is 5. 5 squared is 5 times 5. 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5. 5 times 5 is 25. Now the magic in terms of what everyday people need to know is that 16, which is 4 squared, plus 9, which is 3 squared, is the same as 5 squared, which is 25. 16 and 9 is 25. So that's what we commonly call our 3-4-5 triangle, and I'm going to illustrate the relevance of that in a moment. We're just going to flick over the couple of pages. So here's another example of a right-angled triangle drawn there in the middle. It works, by the way, for any right-angled triangle, but we've chosen the ones here where the answers are in whole number amounts. So if we draw a triangle which is 5 units along there, 12 units along there, and you notice it's a right angle on that corner, that distance there is exactly 13. Now, applying silly old Pythagoras, which we don't need to worry about too much, but let me give you an example. 5 times 5 is 25. 12, that dimension, times that dimension is 144, and that's once again a visual representation of what squared actually means. And this side is 13 times 13. Notice we've gone over the edge just to fit it on the page. 13 times 13 is 169, and voila, 25 plus 144 is 169. So if you don't want to use a 3, 4, 5 triangle, you can use a 5, 12, 13 triangle. And there's another one which we won't worry too much about, an 8, 15, 17 triangle. I think that getting students, by the way, to draw these triangles out with the squared amounts visually represented like I've done there is a good way of helping them understand what squaring actually means. And now finally we're going to go to the really important reason why it's useful to know about either 3, 4, 5 triangles or in this case 5, 12, 13. So we'll move on to the next piece now. So the most common question students ask about anything to do with numeracy or maths or arithmetic for that matter is, who cares anyway? Why would I want to use this? Does it apply in my day job? Who cares? Here's an example of the 3, 4, 5 triangle and the fact that for some people in some jobs it's something they use every single day. So imagine that you are a builder and you're laying out the slab for your house and you want to make sure that when you are laying out the foundations for your concrete pad that it's square at the corners. Builders would take a measurement, they'd measure 3 units, it might be 3 metres this way, and then they'd measure 4 metres that way, and then they'd measure along here 5 metres and make sure that the distance between the 3 metre mark or the 4 metre mark that way and the 3 metre that way, the distance on the angle is exactly 5 and we end up with a right-angled triangle, and we can be 100% sure that that measurement there is a right angle. So farmers use it when they're laying out paddocks, builders use it as I've said, fencers use it, DIY people use it lots of times in the weekends when they're on projects. How else do you find out either if something is square or maybe if something is completely vertical this way? You use the 3, 4, 5 triangle principle to make sure that that distance there is, if that's 3 units and that's 4 units, you can be sure if this unit here is 5 units, that angle there must be a right angle. And if we're talking about this being horizontal, we can be sure that this here is vertical. There's the 3, 4, 5 triangle in action. It works the same whether it's 3, 4, 5, 5, 12, 13, 8, 15, 17. All work very well to get yourself a right angle, which is really, really important. And there's the value, the application of some quite complicated maths into simple everyday situations.